Welcome to part 2 of the electrochemistry video series. In this video, we'll pick up where we left off in the last one, so if you're not sure what a galvanic cell is and how to find and calculate standard potentials, I recommend you go check out the first video before continuing with this one. In the last video, I showed you how to calculate the standard potential of a galvanic cell under standard conditions, meaning 25 degrees Celsius, a pressure of 1 atmosphere, and 1 molar of each of the solutes in their respective half cells. But what if we don't have standard conditions in our reaction? Let's say we have a temperature of 40 degrees Celsius and a chromium concentration of 1.2 molar in the left cell and a nickel concentration of 1.5 molar in the right cell. To our luck, a very smart German physicist named Walter Nernst formulated an equation back in 1888 for the calculation of cell potentials at non-standard conditions. This equation is fittingly called the Nernst Equation and looks like this. Let's take a closer look at its components. We've already talked a lot about E0 cell, so it needs no further introduction. You may also be acquainted with R, which is the gas constant, with a value of 8.314 joules per moles per Kelvin. It can be found in any chemical handbook. T stands for temperature and must be supplied in Kelvin since the gas constant contains Kelvin in its unit. It's easy to convert from Celsius to Kelvin. Simply add 273.15 to the Celsius temperature. We will show a calculation in a minute. N is the number of electrons being exchanged in the reaction, and F is another constant also available in any handbook, namely Faraday's constant. It's equal to 96,485 coulomb per mole electrons. Coulomb is the standard unit for electrical charge, so Faraday's constant is just the total charge carried by 1 mole of electrons. Coulomb is also equal to joules per volt, which we'll see later is a more convenient unit in this equation. Q is the reaction quotient for the reaction. Let's use our nickel-chromium cell to see the Nernst equation in action. We can break down the process into 4 steps. The first step is to find the standard potentials of our individual half cells and from that deduce which cell is the cathode and which is the anode. We'll also calculate the standard potential of this cell. After that, we must write and balance our reaction scheme to find out how many electrons are involved in the process. We'll also use the reaction scheme in the next step to calculate the reaction quotient Q. Then, in the last step, we combine everything in the Nernst equation and calculate the total cell potential. We already performed step 1 in the last video and discovered that chromium is worse than nickel at holding on to its electrons and is therefore the anode placed to the left. We found the standard potentials and we calculated E0 cell to be 0.51 volt. The next step is writing up our reaction scheme, and when doing this, we always write the electron donor on the left in its solid form. The electron donor is chromium, so we write that in its solid form over here on the left, and then on the right we have the chromium ions, and we can see because it's 3+, that it must lose 3 electrons. The electron acceptor must be on the right side in its solid form, so solid nickel is over here, which means that on the left side we have our nickel ions, and we can see that it must lose 2 electrons. You can see that this corresponds to our drawing earlier with the chromium electrode on the left and the nickel electrode on the right. So now we can see that for every time chromium loses 3 electrons, nickel gains 2. The law of mass preservation, however, must be kept, so the number of electrons should be equal in the 2 half-cell reactions. We could solve this by multiplying the nickel scheme by 1.5, but this would end up giving us half a nickel atom, which is not possible. So we must find the smallest number possible, which is divisible by both 2 and 3. This number is 6. To get 6 electrons, we must multiply the top scheme with chromium by 2, and the nickel scheme must be multiplied by 3. Now we can add together the two schemes. So we have all reactants on one side. We have 2 solid chromium plus 3 nickel ions plus 6 electrons. We do the same thing on the right-hand side, where we have 2 chromium ions plus 6 electrons plus 3 solid nickel. The 6 electrons appear on both sides of the reaction arrow, so they cancel each other out. Then we end up having 2 solid chromium donating electrons to 3 nickel ions, becoming 2 chromium ions plus 3 solid nickel. The number of electrons exchanged in the reaction is 6, which is the number n that we must insert into the Nernst equation. The next step is calculating the reaction quotient Q. You may be familiar with how to calculate the equilibrium constant, which is just a special case of the reaction quotient, so the calculation is the same. In general, we have a fraction where the numerator is the right side of the reaction scheme and the denominator is the left side. So if we look at a general chemical reaction where we have A molecules of the substance capital A plus B molecules of the substance B, turning into C molecules of C plus D molecules of D. Then Q can be written as the concentration of C raised to the power of lowercase c, because that's the coefficient in front of C, multiplied by the concentration of D to the power of lowercase d. Then in the denominator we have the left side, so concentration of A to the power of lowercase a multiplied by the concentration of B to the power of lowercase b. However, in practice, we're allowed to omit solids from the quotient. So if we pretend that B and D are solids, then we can omit them from the calculation of Q. So that just becomes concentration of C to the power of C divided by concentration of A to the power of lowercase a. In our galvanic cell, we have chromium and nickel in solid form, so we can omit those when calculating Q. So Q becomes concentration of chromium ions divided by concentration of nickel ions. And then we must remember to raise to the power of the coefficients, which were 3 for nickel and 2 for chromium. Our concentrations were 1.2 molar for chromium and 1.5 molar for nickel. So we can insert these numbers into the calculation of Q. So we have 1.2 molar squared divided by 1.5 molar to the power of 3. Calculating this gives us Q equal to 0.427, and the unit becomes molar squared divided by molar cubed, so that's molar to the -1. We've now calculated all the components we need for the Nernst equation in order to calculate E cell. First we have E naught cell, which is the standard potential, which we calculated to be 0.51 volt. Then we subtract the big fraction here, starting with the gas constant, which we have down here is 8.314 joules per mole per Kelvin. We multiply that by the temperature, which was 40 degrees Celsius. We need to convert this to Kelvin. We do this by adding 273.15, which is the absolute 0 point. Then we get 313.15 Kelvin. Then in the denominator we have N, which was the number of electrons, which was 6, multiplied by Faraday's constant of 96,485 joules per volt per mole. Now we just need to multiply by ln to Q, which was the reaction quotient, and we calculated that to be 0.427 0.7 per molar. Now let's check to see if our units match up. So when we take ln to a number, its unit disappears, so we can ignore the unit from this bit. And then over here we have per Kelvin and Kelvin, they cancel each other out. Then we have joules in the numerator and we have joules in the denominator, so they cancel each other out. We also have per mole in both numerator and denominator, so they cancel each other out. And then we just have per volt here in the denominator, but 1 divided with volt to the -1 is just volt. So the unit for this entire bit here just becomes volt. And over here we have the standard potential in volt, so volt minus volt still becomes volt. So when calculating all of this, we get 0.5138 volt. And this is not far from the standard potential, but it's clear that the more the reaction conditions differ from the standard, the larger this difference will be. And when combining an entire series of cells like we do in batteries, even small differences will accumulate and become substantial. Before wrapping up this video, I'll show you a few useful tricks to make the equation simpler and faster to use on a calculator. Because we have two constants, the gas constant and Faraday's constant, we can just pool them into one. I'll do this by rewriting the fraction here into R divided by F multiplied by T divided by N. So I've just split the fraction in two and rearranged the letters a little bit. Then we can calculate R divided by F by inserting these numbers here. And then we get a value of 8.617 times 10 to the power of -5. This means that our entire equation can be written as E0 cell minus this new pooled constant multiplied by T divided by N, which we have from up here, and multiplied by ln Q. If you prefer log 10 instead of the natural logarithm, we can use the basic rule that says that ln to x is equal to log x divided by log e. And e is the base number of the natural logarithm and has a value of roughly 2.718. We can also rearrange this a little bit to become 1 divided by log e multiplied by log x. If we calculate 1 divided by log e, it becomes 2.303, and then we multiply by log x. Then we have that ln x is equal to 2.303 times log x. So now we can substitute ln q for this right here. Now 2.303 is just another constant that we can incorporate into this constant term just by multiplication, because there's a multiplication sign here. So our new equation becomes E cell equal to E0 cell minus 8.617 times 10 to the -5 multiplied by 2.303 is equal to 1.984 times 10 to the -4. And then we still need to multiply by T divided by N and by log Q now. Lastly, we can make a special case of the Nernst equation for temperatures at 25 degrees Celsius, because there's a good reason this is the standard temperature. It's the common room temperature, and therefore often the temperature at which we perform our lab experiments or at which we operate in a production line. So, if the only deviation from the standard conditions are the concentration of our aqueous species, we can further reduce the equation. First, we convert 25 degrees Celsius to Kelvin, and we do that by adding 273.15, which is our 0 point for the Kelvin scale, and that gives us 298.15 Kelvin. Now we can incorporate the temperature into our constant term here by calculating 1.984 times 10 to the -4 multiplied by 298.15, and that gives us a number of 5.916 times 10 to the negative 2. So now we have a shortened form of our Nernst equation, E naught cell minus this big pooled constant multiplied by log Q divided by N. This form of the equation only has three unknown terms which we must supply in order to calculate E cell, namely Q, N, and E naught cell. On top of that, we use log Q instead of the natural logarithm. But remember, this version of the equation is only valid if the temperature is 25 degrees Celsius.